Welcome, scholars, to National 5 Physics, Unit 3, Section 3, Newton's Laws of Motion. Before we proceed to discovering Newton's laws of motion, we need to make a distinction between the mass of a body and its weight, because they're very often confused. Firstly, the mass. The mass of a body is a measure of the amount of matter that's in that body. It's measured in kilograms, and it's a scalar quantity, no direction. It's really just the amount of stuff that's in the body. Weight, on the other hand, is a measure of the gravitational force with which a body is pulled downwards by the planet that it's on. It's, like all forces, measured in newtons, and is a vector quantity. It has a direction. Its direction is always pointing down towards the centre of the planet. You do a very simple experiment to establish the connection between mass and weight simply by taking a Newton balance, which measures force, and adding various masses to it and recording the weight. A set of ideal results would be like this. You can see there, if we put a 0.1 kilogram mass on, we get a weight of 0.98 newtons. Now, a real Newton balance would have difficulty measuring to 100th of a newton, but these are ideal results. As you can see, the greater the mass, the greater the weight. But interestingly, in the third column, if we divide the weight by the mass for a given body, every single time we get a constant value, 9.8 newtons per kilogram. And this constant is a feature of the Earth. In fact, it's called the gravitational field strength. On Earth, whenever we divide the weight by the mass, we always get 9.8 newtons per kilogram. And so we give it this symbol G, where G is the gravitational field strength of the planet, in this case Earth. To define it, you could call it the weight per unit mass, and it's worth memorising that phrase in blue. It's often asked in exams. So W over M equals G, and we can rearrange that to get W as mg. That's the form the equation is most often written in. It's called the weight equation, and that's the version you'll find in the SQA equation lists. If we plot a graph of weight on the y-axis against mass on the x-axis, you'll see we get a nice straight line. We like straight lines in physics because they're very easy to deal with. They always have the mathematical form y equals mx. That's the equation of a straight line. Y being the y-coordinate, x being the x-coordinate, and m being the gradient of the line here. Don't get that mixed up with mass. At the moment, m is standing for the gradient of that line. Let's clarify that by saying y equals the gradient times x, so there's no confusion. Well, let's translate the mathematical equation, y equals the gradient times x, into a physics equation, because our y-coordinate is weight and our x-coordinate is mass. So we can say weight equals the gradient of that line times the mass. Now that gradient's constant, and in fact, that gradient is the gravitational field strength G. So we end up with the weight equation again, W is mg. So this just goes to show that the graph of W against m helps lead to the weight equation as well. I feel a worked example coming on, so I'm sure you'd like to do one. If you have not done this question before, then pause the slideshow and try it before looking at the solutions. If you have done it before, then this is a revision exercise. You can follow it as we go through. Well, the solution, of course, always begins with our listing of the variables, W, M, and G. Notice, of course, that the 9.8 newtons per kilogram is not given to you. You're expected to know that if you're on Earth, the gravitational field strength is 9.8 newtons per kilogram. You can always look it up in a data table if required, and if it's for another planet, you can do the same. So we state our equation, put in our variables, and then calculate the final answer, 412 newtons. Notice weight is measured in newtons. And we finish off by making a clear statement of our final answer. Now, to recap on the method, and this method applies to all simple equation work, we always begin by listing our variables. That's always step 1. Step 2 is always to state the equation. Step 3 is to substitute in the values. Step 4, calculate the final answer with a unit. And it's good practice to finish by writing the answer in a short sentence. Well, I'm sure you've enjoyed that example, so let's do another one. Andrew has a weight of 390 newtons. What's his mass on Earth? List our variables. Notice mass is the unknown here. State the equation. Substitute in the values 390 equals m times 9.8. A little bit of algebra required now because we need to rearrange for m. Now make sure you can do that rearrangement. This often causes trouble. You've really got to get that rearrangement subconscious. You need to be able to do it without thinking. Keep practicing to do that. And you get the mass is 39.8 kilograms, and it's good form just to put that in a short sentence. So Andrew's mass on Earth is 39.8 kilograms. Okay, we can now proceed to Newton's first law of motion. There are 3 laws altogether. This is Newton's first law. Well, I'd like you to look at that little body down there. He's going to move. Here he goes. Lovely. Now, Newton's first law makes a comment about bodies that move or stay at rest. Here's the formal statement. A body will remain at rest or move with uniform speed in a straight line unless acted upon by an unbalanced force. What this is really saying is that if a body has 0 velocity, i.e. it's at rest, or if its velocity is constant, uniform speed in a straight line, then it follows that the forces on that body must be balanced. So balanced forces means the body's either at rest or it's moving with uniform speed in a straight line. In fact, Newton's first law is often called the balanced force law. Now, I know most of you enjoy going on the hovercraft, but I wonder if you know why it is that the hovercraft moves along the floor once it's been given a little push. Well, I'm now going to explain. The air cushion of the hovercraft, blown down by the blower, acts as a lubricant. The air cushion lubricant separates the hovercraft from the floor. This, of course, reduces friction between the hovercraft and the floor. It doesn't quite reduce the friction to 0, but it certainly makes it much, much smaller. The forces on the hovercraft are therefore balanced, and so once pushed, the hovercraft moves with a uniform speed in a straight line in accordance with Newton's first law. So that's the hovercraft. Now, some examples. Again, if you've not done these before, pause the show and try them first without looking at the solutions. Well, if we look at scenario number 1, we have no forces acting on this body. So part A says, state whether the forces are balanced or unbalanced, and then describe the 2 possible motions. Well, there are no forces acting on this body. The net effect of that is the same as if the forces were balanced. So this body could either be at rest, but it also could be moving with uniform speed in a straight line, We're not told enough information here to know which of those two is in fact the case. It could be either. Number 2, well, we've got 20 newtons to the right and 20 newtons to the left. So clearly here the forces are balanced, and that means that body could be at rest, or it could be moving with a uniform speed in a straight line. Again, we don't know which of the two it is. Either are possible. And finally, the third one, it says, why can't you comment yet on the motion of number 3? Well, that's because if you look at it carefully, we've got 20 newtons to the right, but nothing to the left. Therefore, the forces here are unbalanced. If you haven't studied unbalanced forces yet, you're not really able to comment. If you have studied unbalanced forces, then you will know what the consequence of that is. Let's look then at Newton's second law of motion. So here we have a Formula 1 car flying across your screen. And of course, these are very powerful machines, and that car would experience quite a strong force given to it by its engine. We'll call that the engine force, F subscript E. In real life, of course, it's moving through the air, therefore it's feeling an opposing force due to drag. We'll call that F drag. In fact, there would also be friction in the wheels and in the engine, but we're just focusing on the drag force just now. Now, let's imagine that the engine force, Fe, equals the drag force, Ft. They've got the same size. Obviously, they're in opposite directions, but let's imagine they've got the same magnitude. Then these two forces are balanced. And so the velocity of the car is uniform. You can say constant. We prefer uniform, but they mean the same thing. And Newton's first law describes that situation. Balanced forces, uniform velocity. We're assuming the car is moving. It has to be moving, otherwise there wouldn't be any drag or engine force. Now, what about if the engine force is greater than the drag force? Well, these forces then are unbalanced. And now Newton's second law applies. Let's look at Newton's second law. Newton's second law. Let's imagine a mass, m, subject to an unbalanced force, F subscript un. I'll call that F sub un for reference. And that force, F sub un, is pointing to the right. You do an experiment where you take a mass and you apply various unbalanced forces to it, and you measure its resulting acceleration. Here are some sample results. As you can see, we've increased the unbalanced force from 0 up to 0.5 newtons in 0.1 newton increments. And for each given unbalanced force, we've repeated the measurement 3 times and taken an average acceleration. It should be pretty obvious from this table that the bigger the unbalanced force, the greater the resulting acceleration. Note also that the unit of acceleration is meters seconds to the minus 2. Here's a summary of the results for an unbalanced force acting on a mass. Well, we can plot these results in a graph. So let's try that and see what we get. Well, firstly, we know that the unbalanced force is clearly causing an acceleration. And when a body accelerates, it's speeding up. Here's a graph of unbalanced force on the x-axis with acceleration on the y-axis. Note also that the mass of the actual body that's doing the moving is kept constant. We just use the same low friction car each time. So we can see there that there is a nice relationship between the unbalanced force and the acceleration. It's a linear relationship, direct proportion in fact. Now, one way of describing that relationship is to say that the acceleration is directly proportional then to the unbalanced force, and in symbols, here's how we write that. Mathematically, if the unbalanced force is directly proportional to the acceleration, it follows that the unbalanced force equals some constant times the acceleration. And that constant, it emerges, is the mass of the body itself, m. So we end up with F equals ma. Now, if you look at the graph that's on this screen, we've got acceleration on the y-axis, but this time we're varying the mass of the body, but keeping the unbalanced force constant. So same unbalanced force, gradually making the body more massive. And if we plot the points, they do something like this. You can see that as the mass gets greater, that same force can't accelerate it as much, and the acceleration goes down. When we plot the graph accurately, we get a curved line. Now that's tricky to deal with, so look at this. We have a little trick, if you like. What we do is we plot acceleration on the y-axis just the same as before, but this time we plot 1 over mass on the x-axis, and miraculously we get a nice straight line. Now bringing all of this together just confirms for us that the unbalanced force F sub un equals ma. This is Newton's second law of motion. If you're ever asked to state Newton's second law of motion, then you simply state that equation, F unbalanced equals ma, but you must also identify each symbol. Fun is the unbalanced force, and you must mention its unit in newtons. You must mention the mass, m is in kilograms, and you must mention the acceleration, a is in meters second to the minus 2. F equals ma, Newton's second law of motion. I feel a worked example coming on. Again, if you've not done this problem before, pause the slideshow and try it now. A motorbike accelerates at 2 meters seconds to the minus 2. If its mass is 400 kilograms, find the unbalanced force on the motorbike. Well, we're going to assume that the 400 kilograms is the mass of the bike and the rider. Solution then, we list our variables. F unbalanced is the unknown. Restate our equation. And the unbalanced force on the motorbike is 800 newtons. Now in real life, let's name the two forces which combine to produce this unbalanced force. Well, the two forces are the engine force driving the motorbike forward, but also friction, which always opposes motion. In reality, that friction would be a combination of air resistance and other frictional forces in the wheels and in the engine. Let's do an example then where we have two forces acting just like that. So as you can see, the racing car has an engine force, Fe of 1000 newtons driving it forwards. That's to the left of the screen. And there's a frictional force of 200 newtons. So we'll assume that covers drag, engine frictional forces and wheel frictional forces altogether. If the car has a mass of 1200 kilograms, find the unbalanced force, and then having done that, use it to find the acceleration. So the solution to part A, well, you have to first of all spot that the unbalanced force equals the engine force forwards, take away the frictional force backwards. That's 1000 minus 200, so we end up with 800 newtons to the left. Notice the direction is in red for emphasis. You must always mention the direction when you quote any vector, particularly forces. Part B, well, we now know the unbalanced force, it's 800 newtons. We know the mass, so we can get the acceleration using F equals ma. So we put in our numbers, rearrange for a, and we get 0.67 meters seconds to the minus 2 to the left. Notice the direction required again because acceleration is a vector. And that's Newton's second law in action. The third and final of Newton's three laws, Newton's third law. I want you to imagine you're leaning on a wall with your hand, pressing on the wall with your hand. What you can see in front of you there is a situation diagram showing you the bodies and the setup. There's a hand, I admit, rather strange looking hand, but it's quite tricky to draw. And it's pressing on the wall. So we've got a hand pushing on the wall there. Well, first of all, notice there are two bodies involved here, the hand and the wall. That's going to prove to be important. Now we're going to draw what's called a force diagram. In the force diagram, we show the forces. So there you can see the force of the hand on the wall, that red force. It's pushing the wall to the right. And we're going to call that an action force. So the action force is the force of the hand acting on the wall. Now what Newton discovered was that when the hand pushes on the wall pushes back on the hand. And that's called a reaction force, wall on hand. So we have the action force, the hand on the wall, causing a reaction force, the wall on the hand. Now, whenever you establish an action force, you will always have body A acting on body B, hand on wall. It's very easy to get the reaction force. You just invert the two objects or two bodies. So rather than action force being hand on wall, the reaction force simply becomes wall on hand. And here it is in summary. Well, Sir Isaac Newton summed this up in his third law of motion. And it is, for every action force, there is an equal and opposite reaction force. That is Newton's third law. Notice you should always say action force and reaction force. Some textbooks miss out the word force and just say action and reaction, but it's always more accurate to put in the word force for each of those. Let's make a couple of observations. The first one is, whenever you've got a Newton 3 situation, that's Newton's third law, there will always be two bodies involved. Just as above, we have had the hand and the wall. Newton 3 forces always come in pairs. And here's the bit that often causes trouble. The two forces act on different bodies. Think about that. The two forces act on different bodies. Look at the diagram. The action force is the hand acting on the wall, whereas the reaction force is the wall acting on the hand. The forces are acting on two different bodies. That is Newton's third law. We're now going to apply everything you've learned on mass, weight, Newton's first law, Newton's second law, and Newton's third law to the launch of a rocket. A very favourite scenario in National 5 exams, and a very interesting one because in sending the Apollo astronauts to the moon in the 1960s and 70s, all of Newton's laws were crucial to the calculations. You might want to enjoy looking at that picture. This is a very famous picture. It's of the Saturn V rocket launched in 1969. And although you can't see them right up in the nose cone there, you would have found the three Apollo 11 astronauts. Let's analyse rocket motion. Well, a rocket is really just an empty container in which gases, which are usually stored in liquid form, compressed into liquid form, are allowed to burn and become gaseous. Now, if you've got on average 1 litre of a liquid and you burn it into a gas, it becomes about 1,000 litres. There's a volume expansion of about 1,000, but there's nowhere for the gas to go inside the rocket chamber except out the back. And at the back of a rocket, there's really just a hole at the back to let the gases out. So what happens is the gases burn, and for example, it could be hydrogen and oxygen burning together, and they come flying out the back. They get forced out of the back. So we're going to think of the situation here as involving two bodies. The rocket itself, but also the exhaust gases that it emits. Now, some people don't think of gases as being a body because they think of gas as being very light, but in fact, the gases in a real rocket have many millions of kilograms of mass. So, two bodies. Well, if you look at the diagram, we're going to consider the action force here as being the rocket forcing out the gases. So the action force is to the lower left of the diagram there, the rocket on the gases. Now, once we've established the reaction force, rocket on gases, it's very easy to get the reaction force. We just invert the words and we get reaction force, gases on rocket. Now, it's that reaction force, gases on rocket, that actually makes the rocket move. And this is Newton's third law, of course, action and reaction. We normally call this reaction of the gases on the rocket the thrust of the rocket engines. Remember, only forces acting on a body affect a body's motion. Forces exerted by a body don't directly affect its motion. So, a question. Does the ground have anything to do with rocket motion? If you haven't answered this before, pause the slideshow and have a go. The answer is no, the ground is not involved at all. Rockets can work in space, nowhere near the ground. So don't fall into the trap of thinking that somehow the exhaust gases push off the ground. I think because you see this in rocket launch films, you think that somehow the ground is involved. But the rocket keeps going even when it's nowhere near the ground, so the ground's nothing to do with it. I feel an example coming on. Here we have a rocket of mass 20,000 kilograms, including fuel and payload, is launched vertically upwards. If the rocket exerts 20 kilonewtons of thrust, calculate the acceleration as it leaves the launch pad. Well, in tackling this one, firstly notice there is text in the question but no diagram. And when you get to these fairly complex problems, you really need to draw a diagram. So the solution begins by drawing what's called the free body diagram. And here is the free body diagram. A free body diagram involves the object of interest, the thing that's doing the moving, and in this case it's the rocket. So I'm going to put in my rocket there with the thrust force of 20,000 newtons. Always write the name of the force next to the arrow, and if you know the value of it, put it in. But of course, that can't possibly be the only force acting on the rockets. It has weight. So we need to acknowledge that weight is acting. We can also put at the side a little A with a double-headed arrow to show that it's accelerating upwards. We know that because it's being launched. Having done your free body diagram, and remember a free body diagram is the diagram of the object of interest with all the forces acting on it, but no other bodies. Second thing to do then is to set up the force equation and put in the data. Well, we've got these two forces. We know that the rocket is moving upwards, so let's assume that it's accelerating. That's why that double-headed arrow is there. So the unbalanced force upwards must be the thrust acting upwards, take away the weight acting downwards. Well, we know that there are 200,000 newtons of thrust going up the way, and we take away from that the weight, which is mg. That's the 20,000 kilograms times 9.8. So we've got our 200,000 newtons minus 196,000 newtons. The thrust has won, if you like, by 4,000 newtons. So the unbalanced force is 4,000 newtons. That's what's causing the acceleration. So we have to calculate this acceleration. We now apply Newton's second law. F equals ma. 4,000 is 20,000 times a. Algebra again required to rearrange for e. That rocket is accelerating upwards at 0.2 meters seconds to the minus 2. This last section of 3.3 allows us to have a look at some safety features of modern cars. That would mainly be the seatbelt and the airbags that are now common on all cars. So let's consider a situation where we have a driver of a car. You can see her there, and she is indeed wearing her seatbelt. So we're going to consider a situation where the car crashes whilst the driver is wearing a seatbelt. Well, in the upper diagram, you can see the car is moving along with a nice uniform speed. Everybody is happy. Nothing really to write home about there. However, in the lower diagram, the car is either braking very heavily, because it's an emergency stop, or it's crashing. Now, when that happens, the brakes exert a very substantial opposing force on the car and causes the car to decelerate. And that opposing force, that braking force, is transferred through the seatbelt to the driver. And that red arrow there shows the force exerted on the driver, which is transferred to her through the seatbelt. The consequence is the driver decelerates to rest with the car and is safe. So that's what happens when the seatbelt is worn, as it must be nowadays by law, in this country at least. Now, I'm sorry to say that when I was young, it was not. Nowadays, in addition to seatbelts, we also have airbags, and they're particularly good, even if you are wearing a seatbelt, because the seatbelt will slow you down to an extent, but you still get thrown forward a bit before the seatbelt activates. And when the seatbelt's in use, it has to exert quite a big force on the body in order to produce the very rapid deceleration required. Newton's second law shows you that. If m is the mass of the driver, or the passenger, the person slowing down, if it's a very abrupt deceleration, then the A in the F equals ma equation is very big. Now the mass is constant, so if A is big, then the decelerating force must be very big, and that's what is provided by the seatbelt. Now if you include an airbag, the airbag basically increases the time of the deceleration. It acts as a sort of cushion, and it still brings you down to rest, but in a slower time than you would otherwise. Now, if you think of your acceleration equation, a equals v minus u over t, well, the final speed v is 0. So if we put 0 into that equation, where the v is, we get a equals 0 minus u over t, or just a is minus u over t. So if the speed then initially is u, that's a constant, you're travelling at say 30 miles an hour before the crash. If you can increase t, you make the deceleration smaller, because your initial speed u is fixed, so a bigger time of deceleration decreases your deceleration. And that's the reason for having an airbag. A smaller deceleration means a smaller decelerating force, F equals ma, remember, and that's obviously beneficial to the wearer. And there we are, the end of Unit 3, Section 3. I hope you have enjoyed the slideshow. Toodle pip.